Okay, so just one more time. Again, we're going to have this tutorial session in the morning for people who are not familiar with Nars, going into some simple hands-on examples, and then in the afternoon, we're going to have a workshop for more advanced Nars topics. So here's the schedule for today. We're going to start off with an introduction to Nars non-axiomatic reasoning system, and more specifically, actually, the logic of the system. And then we'll go into the actual AI system itself and the real implementation, which is what Bowen will talk about. Then we'll take a short break, and Bowen will go through some reasoning examples using the real implementation, followed by a short example of a real-time application using Nars Palm. And Patrick will follow that up with hands-on examples, more advanced hands-on examples using Nars. And then we can have a more general discussion and question and answer. Sound good? Okay. On that note, I'll jump right into the intro to Nars. So first, what is Nars? Non-axiomatic reasoning system, or Nars, is an AGI project, which is why we're presenting here at the AGI conference. And what that means is that unlike modern mainstream AI, the field of AGI emphasizes more the holistic and general nature of cognition, which we see best in humans, which, as we've seen, are basically capable of accomplishing anything we set our minds to, and conceiving of nearly anything, a very general capacity. And while many AI systems are usually oriented towards optimizing task accuracy in one domain, for example, like scoring the best image classification on certain benchmarks, Nars is open to solving any task which we assign to it, no matter which domain. So in this way, we can say that Nars has something like a basis for general intelligence, similarly to a human, because for us, we can take any single Nars agent, at least theoretically, and have it work across any number of domains across its lifetime. And so in the design of Nars, we use a working definition of intelligence. We don't just use the word intelligence. We want to more concretely define it, and then we use this as a basis for the system design. And so we define intelligence to be the capacity of a system to adapt to its environment while operating with insufficient knowledge and resource. And by adapt to environment, it means to learn and accomplish goals in that sense. And so this definition of intelligence then gives us a design assumption, which is the assumption of insufficient knowledge and resources, or AIKR. And so when we say that we have this assumption, or when we say that the system has insufficient knowledge and resources, what we're meaning is that the system relies on constant finite processing capacity. It's not constantly needing more resources as it grows and learns. It always operates using a constant processing capacity, like a human brain. Works in real time, so you don't have to sit around waiting for to query the system or something. It works in real time. And it's also open to knowledge and tasks of any content, and that's the general part of the system. And that's to say that Nars is not restricted to any one domain. As long as you can say it to the system will process it and understand it to the extent that it can. And as a consequence of this assumption, the system itself has no overarching or objective benchmark, or like fitness function or loss function, which the system measures its learning or its correctness or optimality of its behavior. And so instead the system measures its correctness based on how well it's meeting its personal goals. The system itself has its own goals, its own set of goals. It can be very disparate. And so instead of using an objective function, the system processes its information and makes decisions based on the evidence that is available. And so this way, the system is more general, adaptive, flexible, and robust. So when we say non-axiomatic reasoning system, what is a reasoning system? It's more traditional form of AI system. Nars is a more modern iteration. And there's 5 components to any reasoning system. So it'll have a grammar or language, and this is how you represent knowledge in the system. It has a set of logical inference rules, and it uses these to reason over the knowledge. There's a semantic theory, and this is basically the theory behind your system. What is your justification for why the system is expressing sentences with valid meaning? Why are those meaning valid? Basically, explanation of simple grounding problem. Finally, a memory structure, because the system needs to store the knowledge in some sort of memory, and a control mechanism which it uses to select knowledge for using those inference rules. And so I've highlighted these first 3 components here because that's what we're going to focus on, at least in this presentation. And so in Nars, these are we kind of branch these all under the umbrella of non-axiomatic logic. These first 3 components all fall under the logic, and this is the logic by which Nars operates. And then components 4 and 5 are basically how do you take the logic and put it into a real computer algorithm so that it works. And that will be in the next presentation. And so why use a reasoning system compared to other AI? Good question. There's the potential for domain independence, like we just said. If your knowledge representation is flexible, then it doesn't need to be restricted to any domain. And this allows for your generality or general intelligence. A rule-based language using like inference rules, things like this, it provides rich expressive power and also human understandability. Because when you're doing reasoning, this is sort of how humans think. We make justifications for the things that we do, even if they're not necessarily objectively good or objectively good justifications. We all have justifications for our behavior, and so we can best understand reasoning systems compared to something like a neural network. Logic-based reasoning justifies the system's thoughts and actions past mere mathematical optimality. So the system can say, this is why I did what I did, not just because it optimizes this loss function, but because of these reasons, and which humans can understand. And then finally, we have flexibility in combining these inference rules. So if you have a very small knowledge base, the system can take just this very small set of knowledge and derive many possible conclusions just using these different inference rules. So here's the layers of the logic, of non-axiomatic logic. And by layers, we just essentially mean that, we want to explain the logic in a way that makes sense, kind of simple, and then kind of build on the material. And so like now 1 is like the bare minimum of what you need for like a very, very simple version of the logic. Now 2 is like a more advanced version. And then we kind of build on the material up these different levels. And so in this presentation, we're going to cover all the way from now 1 to 8, but it's primarily going to be now 1, which is where the real meat of the logic is. So first, what you need to know is concept. So this is basically the ideas in Nars. So Nars memory, this is what is inside Nars memory. It's many, many concepts. And so on its own, a single concept doesn't mean anything. Instead, it gains its meaning through its relation to the other concepts. So this is the semantic theory of Nars. So when a concept doesn't refer to something in the outside world, it only means something in relation to the other concepts that the system has learned. So everything is relative to what the system has seen up to this point, and then it can compare different concepts. And so we use a word called a term to name each concept. And so a term can be anything, because like I said, a concept it's not necessarily representing something in the outside world. So it doesn't have to be like a cat, like the word cat or something like this. It can be complete gibberish, as long as the concepts are entering the system in a way that it can associate them properly. The term can be anything. It can be like ASDF 1, 2, 3. But the benefit of using a reasoning system is the fact that it's more human understandable, right? So you can use a human understandable word like cat or dog or apple, whatever it is. And so with these terms, you can build statements, and these are essentially the knowledge in the system. So a term names a concept, and then these statements describe relationships between terms or concepts. And so a statement has the form subject and copula, the predicate. So subject S, copula is this arrow, and then predicate is P. So S and P, the subject and the predicate, are terms, which are naming concepts. The copula is inherent to the logic, and it describes the relationship between the concepts. So here it's describing this arrow, this copula is describing a relationship between S and P. And the fundamental copula in Nars is this arrow. It's called the inheritance copula. And it describes a specialization generalization relationship. So something like water is a type of liquid is what that sentence means. So the water is a specialization of liquid, right? And the liquid is a generalization of water. And so the subject in an inheritance statement like this is like a more specific example of the predicate, and the predicate is more general. And the properties of inheritance copula is that it's reflexive, which means that a term inherits itself. So water is a type of water, technically true. And transitive, which means inheritance will hold across ordered terms. So if you have an ordering such as raven is a specialization of bird, and bird is specialization of animal, then using the transitive property, you can say, okay, well, a raven is clearly a type of animal. And so that's deduction. And so these statements represent relations, but by themselves are not terribly useful. So we add punctuation to them to make it a sentence. And basically what this means is that it can have a truth value. And so it could be true or false. So if we add a period to this cat as an animal, then we could say that this statement is true or false. And the period in this case, there's a period at the end of this, is the punctuation that denotes the sentence as a judgment, which just means it's a piece of knowledge about the world. So there's three types of sentences. There's judgment, which is the period. It just means like a piece of knowledge or a fact. There's a goal, it's this exclamation point as the punctuation. And it's a statement that Nars desires to make true. So for example, this is a goal saying Nars wants to put the coffee in the cup, which is good. And a question is the final type of sentence. This has a question mark. And when you put this into the system, Nars will try to find the answer if it doesn't already know it. So you could ask Nars, is a human an animal? And it could do some reasoning, some sort of backwards reasoning to try to say, oh, I don't know, is a human an animal? And compare like the properties of humans and animals. But a sentence is not only true or false, objectively true or false. Like we said, everything is relative to the system's experience. Nothing is declared entirely true or false by us beforehand, before the system operates. It's all decided at runtime based on the system's inputs. And so the system will receive a stream of information, and this is its experience. It's a stream of sentences, and it's input to the system constantly as it's living. And then, so this is K, this set here, if you want to consider it a set of the stream, a set of sentences. And then the system will then derive beliefs from this stream of experience. And this is essentially the way that the system can derive new knowledge that it's not directly been given. And it's the transitive closure of K, which we discussed a transitive property in which we can connect unconnected terms that were originally unconnected and then connect them. Using the transitive property. And so that's basically how Nars gets its many beliefs, is by doing this sort of connecting between different terms over and over. And so, like I said, in this way, the system's beliefs go beyond its experience, and it's actually reasoning about what it's experienced and producing new knowledge, even if the experiences seem quite different. And so that's why we call it systems beliefs instead of like facts or something, because this is just simply what the system believes. It's not something that we can take to be 100% necessarily true or necessarily false. It's just simply based on the system's experience and what it has been exposed to. So it could be completely wrong if it's been exposed to incorrect experience, taught incorrectly, or it simply doesn't have enough knowledge about the current situation. Now, of course, it's kind of reductive to say that any statement is actually entirely true or false. You can't say that about many statements. And so often the truth is a matter of degree. So what do we do in Nars? So first I'm going to introduce a couple of concepts called extension and intension. So if you have some term T in the center here, it's going to have an extension, which consists of terms, and an intension, which also consists of terms. And the extension, and again, thinking in terms of the inheritance copula, which is the fundamental relation in Nars, the extension is all the terms that inherit T. So here, if you can read set notation, it says the extension is the set of all X such that X inherits T. And conversely, the intention is the other way. It's everything that T inherits. So the intention is the set of all X such that T inherits X. And you can see these dotted lines kind of show you what that means. And so in plainer terms, it means that examples of the subject are also examples of a predicate, and the properties of the predicate are also properties of the subject. And using these intention and extension, now we can begin to define evidence, which is what the system will use to justify its beliefs. So we have positive evidence, which is knowledge or evidence in support of a statement or a sentence. And then we have negative evidence, which is evidence against that. And so this is basically how we determine truth and false. So if there's lots of positive evidence, the statement is more true. There's lots of negative evidence, the statement is more false. But it is a matter of degree. So to compute the amount of evidence, you take the intersection of their extensions. Well, this is the formula. These are the mathematics, which you can dig into after this if you like. I don't think we have the time. But essentially what's happening here is that if there is some term that inherits both S and P, imagine this green plus sign here is some term. You can see my cursor. This green plus sign is some term, and it's inheriting both S and P. So it is an instance of both S and P. So it's positive evidence that S inherits P, or P inherits S. But in this example, we're doing it in this order. And similarly, if both of the terms S and P inherit some other term, the same term, which is this green plus sign up here, that's also positive evidence. Because essentially, if the same thing inherits both terms, or they both inherit the same term, obviously those terms must be somewhat similar in themselves. So those are positive evidence. 4S inherits P. And then negative evidence is evidence against S inheriting P. So if something inherits S but not P, something is a type of S but not a type of P, again, using that transitive property, it should inherit P if they're similar. And since it's not, it's a piece of negative evidence. And similarly, if P inherits something that S does not, P has a property, S does not have that property, well, then again, it's evidence against S inheriting P, since S does not inherit that property. So this is negative evidence. And then you can sum up the positive evidence, sum up the negative evidence, bring them together, add them together, and you get your total evidence, which is the magnitude of the extension of S plus the magnitude of the intention. So yeah, traditionally the truth value of a sentence represents how much does this sentence agree with reality as humans understand it, as human knowledge. How close is it to an objective fact as determined by the humans? But in Nars, it's not quite that way. The truth value is measured based on the evidential support. Now, the evidence is supplied by humans initially, or at least, if you hook a sensor up to it, you as the human designer or as the human operator of the Nars system are giving it certain sentences. But from there, Nars will take the evidence and put it together on its own. So a truth value in Nars is a pair of real numbers, FC, which are F is in 0, 1 inclusive, confidence is, or C is in 0, 1 exclusive. So F means frequency, and it's like the traditional understanding of truth. So if you have a frequency near 0, you might say, oh, this statement is pretty false. If you have a frequency near 1, it means, oh, this statement is pretty true. Confidence is the total amount of evidence that was taken into account when determining the truth value. So the way you calculate the frequency is the positive evidence over the total evidence. So this is like when you take everything into account, well, all the evidence for the statement, how much of it leans towards true, and that's the frequency. And then how much, since Nars will not take everything into consideration due to resource limitations, you also have this confidence value, which determines, okay, well, how much evidence do we have to, how much confidence and evidence do we have to support this frequency value? And so it really is the system's confidence in the statement. So the actual experience is a system receiving a stream of sentences from its sensors. You could have a human sit at the computer and type in sentences all day. Actually, probably will be better to just connect a sort of sensor to the system and have the sensor automatically produce those sentences for you. And each sentence will be input with a truth value, including frequency and confidence. And from there, the system uses truth value function, essentially a function over these truth values to determine the new truth value of the result. So every time it does reasoning, it's going to take 2 sentences. Each one has a truth value, put them together, determine the new truth value and the new result. And so we're all familiar with the traditional Boolean operators if you've ever programmed. So there's not, and, or. And from here you can say, oh, based on the truth, this true or false of the premises, we can determine the true or false of this operation here, of this operator. But in Nars, since we have this continuous valued logic between 0 and 1, continuous valued truth value, I should say, we extend the Boolean operators, but while still constraining them within 0, 1. So to negate a truth value, you simply take 1 minus the value. And is a multiplication of the values, and or, similarly, it's a, well, if you know or, it's a not and. So that's what that is. So we're going to run through the basic types of inference. There's deduction, induction, and abduction. So if you have 2 premises, like S inherits M and M inherits P, as we discussed earlier by the transitive property, you can derive S inherits P. And we use a truth value here to determine, we use the function here to determine the truth value of the result. So you take the frequency of the premises, you multiply them, or you AND them. You take the confidences and frequencies, and you AND them to get the confidence of the result. So for an example, you could have a robin is a bird and a bird is an animal. You derive a robin, excuse me, a robin is an animal using deduction. And those are the values. And this is what it looks like sort of visually. So those dotted lines are the premises, and that solid line is the conclusion. Induction is essentially the a generalization that one makes. So if you have here M inherits P and M inherits S, you can take the 2 more general terms and produce a new sentence by what we call induction that says S inherits P. And similarly, we have the truth value functions here to determine the frequency and confidence. And for an example, you could say a swan is a bird and a swan is a swimmer, you know, say something that swims. And so you might say that to some degree, birds are swimmers, at least to some degree. Not all birds are swimmers, but some. The other way around, abduction, is comparing more specific examples with each other. So if you have P inherits M and S inherits M, then you can, again, derive S inherits P. You can see the visualization of this and the truth value functions. And as an example, we would say something like, okay, a seabird is a swimmer and a gull is a swimmer. And so we can derive that a gull is a type of seabird, just based on that knowledge. And so from here, we're taking two things which share a property, two concepts which are swimmers, and we say they must be similar in some way.
Questions, Jerry?
Sure, yeah, absolutely.
How do you determine the direction of that? Not that a gull is a seabird and not the other way around, a seabird is a gull.
You can do both directions.
Okay.
Here, this is just the one. But yes, it does go in both directions. And then finally, the revision rule, which is a special type of inference rule, which we use since we have this concept of evidence and the quantity of evidence, and like how much evidence are we using. And so when you have two sentences which have the same statement, we're not deriving any new knowledge here. It's the same piece of knowledge. They just have different truth values. Perhaps they were given from different sources, or they're based on different evidential base. So we combine them together. We combine their evidences together, and using this revision rule. And so we get a higher confidence since we're using more evidence in the calculation. So every time you do a revision, you will always get a higher confidence. Now your frequency might be different because, again, frequency is something like truth. So here, if we have a bird as a swimmer is true and bird as a swimmer is false, two different people telling Nars different things, then Nars will have to put them together and say, oh, bird is kind of a swimmer. Taking them to be and weighting them based on their confidences. The frequency is weighted based on confidence. So if it's more confident, the frequency will lean in the more confident direction. So in summary, there's three types of inference. We have the local inference, which is like that revision that we just showed, which is essentially just taking your beliefs and improving their confidence, improving their quality. Forward inference, which is the basic form of inference that we all know and love, deduction, induction. So given this, these two pieces of knowledge, how can I, thinking forward, how can I derive new knowledge? And then backward inference, which is based on this answer, doing inference backwards, based on the conclusion, what would be the premises? So basically doing the inference process in reverse. And that's useful for, like we mentioned, questions and goals. If the system has a question and it doesn't know the answer, it needs to do backward inference to say, okay, well, what do I need to answer to get this answer? So that was now one. That's the meat of the presentation. And now we're going to go into the higher levels of the logic, but only the very, very basics. So in certain cases, you can use special variations of this inheritance copula just for succinctness in writing or succinctness within your system of representation and like reasoning. So as mentioned before, sometimes the inheritance can go in one direction and also the other. And when this happens, it's not necessarily that S is a generalization of P or P is a generalization of S, it's sort of both. Or rather that neither is a generalization or instance of each other, they are just both very similar, rather than a true specialization generalization. So we can use the similarity copula to represent that. So something like Pepsi is similar to Coca-Cola. Pepsi is not a type of Coca-Cola, and nor is Coca-Cola a type of Pepsi. They're both types of cola, but they are not, they're similar to each other in that regard.
I have a question.
Yes.
Previously, when you looked at the values, like I'm thinking you can assign, like there is a thing object done, you assign a value that this is true. And does it matter how many times, like if like 10 people are saying this is true, like 100% doesn't matter, or is it just one like that line? Or it's good to have like many people who say the exact same thing and give the same value in a sense.
So it's based on the confidence. So you could have many people say something, like say as an input to the system, with very low confidence. And then you could have one person input something to the system with very, very high confidence. And that will, when it's combined, the higher confidence will take a higher weighting, a higher priority. Although the other 10 lower confidence will be taken into consideration as well and skew the truth value in a certain way. If the higher confidence one goes in a certain direction, it will skew much more strongly in that direction. So it's not necessarily the amount of sentences that are entered, but really how they're weighted with the confidence. Does that answer your question?
Yes, it does. Well, is there like an optimal how many frequencies you need, or like these are hundreds, thousands, or there is a limit?
No limit. Now, of course, you're going to get to some point where like you're increasing your confidence up to the point where it's like 0.9999999, and like you can't, like you add another 9 at that, it doesn't really matter. I don't know. Not really, but there are parameters that you can use to say, like, we need much, much more evidence to get to that 0.99999. So you can set it, you can configure your system in that way such that it will never really max out. Yeah.
Maybe you'll
Yes.
cover it later, but will the system be able to track the source in the final output? This is where how the truth value came or what the reasoning.
Yes.
So will it be able to cite the source?
Yes. So while it's not technically in the logic, in the implementation of the system, we store what is actually technically in the logic. We keep track of all the sentences, like you said, that were used to derive the premises. We call this the evidential basis. So it's basically a list of all the sentences that were used up to this point to derive this final piece of knowledge. And we do this because if you take the same piece of evidence into consideration multiple times, you're going to like you can't take the same sentence and revise them together to get a higher confidence because it's the same piece of knowledge. So you don't want to take the same evidence into consideration multiple times. It results in what's called circular reasoning. And so in that way, you need to make sure that when you have two premises, their evidential bases are distinct from each other. Good question. Thank you. So the other types of copulas are instance and property. So when the subject is an instance, which is the most extreme form of a specialization, then you can use this instance copula if you want, or you can put it in these curly braces. So for an example of an instance like Bob is a student, there is no further specialization of Bob. Bob is the furthest specialization you can get. And conversely, with the property, it's the other way around. So if the predicate is a terminal property or a terminal predicate, it's the most extreme form of a generalization, then you can use this property copula, or you can stick it in these square brackets. And so an example of that would be something like the sky is blue. Now you might say, oh, but blue is a color. Blue inherits it would inherit color. Well, the concept of blue is not exactly the same as the blue in the brackets. The concept blue is the concept of blue, and it would inherit color and things like this. Whereas the blue in the brackets means more like like describing things which are blue. And so you can't get more general than that when you're describing simply the blueness of objects. So up to this point, we've only talked about atomic terms. So things like S and P, these are just single words. And this is, as we've seen, it can be pretty useful for describing knowledge, but it only results in very simple sentences and concepts. And we can introduce the principle of compositionality into the system by allowing the compounding of terms together into a new term. And we do this using term connectors. And the resulting term will have a different meaning that is related to the meaning of its constituent terms. So for example, you can take the extensional intersection of two atomic terms to create a new concept. And what this does is, as it suggests, it takes the intersection of S and P's extensions. What do I mean by that? You can have the compound like this, yellow property yellow and bird. And this is a concept which represents yellow birds. So you can see how we're taking the two concepts and we're putting them together to create a new concept. We have yellow, we have bird, now we have yellow birds. And from this, the system can infer a statement like a canary is a yellow bird. If it has a canary, it's yellow. I saw a canary, it's yellow. I saw a canary, it's a bird. So I saw a canary, it's a yellow bird. So you can see how the system is producing new knowledge based on this very simplistic initial knowledge. So compound terms, that's now 3. Now 4 is about introducing arbitrary relationships between terms or concepts. So we've talked about inheritance. It's very useful, especially we're talking about like general intelligence. We're providing something which provides a specialization, generalization relationship. Something is more general than the others, but we can't specify arbitrary relationships, which might be useful. So we introduced this product term connector. This is product. And if you use the product with the inheritance copula, we can represent any arbitrary relationship. So if we want to say water dissolves salt, that's how we would say it. Water product salt inherits dissolve. So you take sort of like the first term, water, then you move to the predicate, dissolves, then kind of back, salt. So that's how product works. And the dissolve is the relation. And you can deconstruct the product by moving the terms around to the other side using a different connector, which we call image. And then from there, you can say, you can derive new concepts such as water is something that dissolves salt. Yeah. And so this term itself has its own unique meaning, something which dissolves salt. So now the system has a concept when, if you say water dissolves salt, now the system can derive a concept of things which dissolve salt, which is not just water, it can be other substances. So we mentioned putting atomic terms and constructing statements or sentences out of them. And we call those the first order statements. But we also want to allow higher order reasoning, which means that we want the system to be able to form statements about statements. So we introduce a new copula called the implication. And what this allows is the truth of a statement to imply the truth of another. So it's not necessarily relating truthiness, but, semantic content, but relating to the truth of the two statements. And it's sort of like an if-then statement, if that helps you understand. So when S implies P, what it's saying is when S is true, P is true. If S is true, then P is true. For example, if the light is red, then the oven is hot. Don't touch it. Or if the light is red, it implies the oven is hot. It's implication. And so just like the atomic terms, you can take statements and connect them with each other, treat each statement like a term by itself, except you use a special set of connectors to connect statements with each other, but they're treated effectively the same. Up to this point, we've only discussed constant terms, which means that each term names a specific concept. So cat the term cat will always point to the concept of cat. One and only one concept. But there are certain cases where we want to represent knowledge, but the exact concept within that knowledge is not known, or it doesn't necessarily matter. And so in those cases, we use variable terms. And this is very useful for deriving generalized knowledge. So an example of a query variable, or a query variable is something which is a variable which is used to ask what term belongs in this sentence. So we could say, what is a red bird? And then Nars can try to figure out, using reasoning, what is an example of a red bird, and then we'll spit that out to the user. An independent variable which is this hashtag X or pound X, represents any term under the given restriction of the knowledge in question. So for example, this X here, this sentence here says, if X is a type of dog, then X is a type of mammal. So whatever X is, the system can conceive of whatever is X. If it's whatever this X thing is, if it's a dog, then it's a mammal also. Now we're going to move into temporal reasoning. Up to this point, we've discussed how Nars can sort of take encyclopedic knowledge or book knowledge and put it together. But as we discussed the system, we want the system to work in real time, and especially in real-time applications, such as robotics. And so we need to have some sort of temporal reasoning so the system can figure out the consequences of its actions. Like it presses a button, does something happen? So what we do is we can allow judgments to have a timestamp associated with them. So in that case, we call the judgment an event. And this is usually what the system will receive from its sensors. So it might receive an event like at time t=1, the sky is gray. And then at time t=2, it might receive another event which says the weather is raining. So now when we do reasoning, we account for the time steps. And so in the simplest case, we just associate the two events using a predictive implication, which means this event preceded this event, or one event came after another. And this allows Nars to make predictions. So in this case, with our examples, taking these two sentences and using them temporal inference, we can derive an implication statement. If the sky is gray, then later the weather will be raining. And so this is how the system makes predictions. And finally, we're at NAL 8, which is operation and goals. And up to this point, we've only discussed the internal mechanisms of Nars and how inputting knowledge into Nars works, and then how the system reasons over it internally. But the system is an agent that we want to interact with the world. And so it needs an external mechanism to actually do that, which actually allows the agent to output information or move some motor or something like this. Yes.
How do you update the knowledge? Like at some point, for example, temporal, initially the belief was Earth is flat. And after some time, new research. So how do you negate that? How do you say that the old knowledge is like invalid?
So the system might have a piece of knowledge that the Earth is flat.
Yeah.
This is what it thinks, and it has a frequency of 1, so it believes this to be true. Then you can come along and put into the system, the Earth is not flat, and give it a frequency of 0, which, saying it's false, and give it a very, very high confidence. And then it will revise those two beliefs with each other. And since you gave it the belief that the Earth is not flat with a very high confidence, then it will weight that statement or its belief in that direction more strongly. Does that make sense? So essentially, the system is constantly revising its beliefs and determining new truth values for them. So there's, yes, of course.
How do the model represent time? For example, it thinks it's about to rain. So is it represent a distribution of the raining probability, or just a specific time t to represent the t1? After t1, it's about to.
So the way, that's a good question, and it's sort of a tricky point. Like, how do you represent an event? Do you represent when the event starts, or in the middle of it, or towards the end? Like when it's raining, like how do you put that into the system, or when do you put that into the system? In the middle of the rainstorm, at the beginning? The way we do it is at the beginning of the event. or at least the system is receiving a stream of experience. And so it'll constantly be receiving information like it's raining. But basically we take it as, a single time step, like a t equals 1, t equals 2, t equals 3 with each sentence. So it will have, one number associated with it, which is the time. And so an earlier timestamp will come before a later timestamp.
When the new knowledge comes, when we first, for example, like when we inputted the earth is flat, we will input at that point with a high confidence because that's the knowledge at that point in time.
Sure.
And then the next one comes, that also has the high confidence because now, so how do you, how does that replaces and what would it take to replace the old knowledge with new? For example, like this new president got elected. So that president, that's the truth. Okay, got elected with a high confidence. Then the next one got elected. So how does it know like which is the current president?
Well, it depends on.
Both had high confidence at that point in time.
I agree. It depends on the design of your system, how it decides to treat old knowledge and new knowledge.
Okay.
You could, for example, flush out that old knowledge just by sort of putting that new information into the system many, many times, or with an even higher confidence than the old one. It depends on the actual Nars mechanism that you're using. How does it decide to treat prior knowledge with new knowledge? So returning to operations, there's a special type of term called the operation, and this is how Nars performs external actions. So you might have an operation like jump. And so Nars can, when it selects this concept or thinks about this, so to speak, then Nars can jump. So if you have set up your Nars with some sort of robot, it has some sort of motor actuator that allows it to execute a jumping motion, then when Nars executes jump, then the operation can trigger that motor, launch the robot up. But we don't want Nars to execute the operation every time it thinks of it. That doesn't make any sense. We only want it to execute the operation when it wants to execute that operation, when it makes sense to. So we introduce goals, which is the basically how the direction of the system. So we can input this goal like Nars wants the door to be closed. And it might have some knowledge, well, if I slam the door, then the door will be closed. And so using backward reasoning, it says, oh, I want the door to be closed, so I should slam the door. Hopefully it doesn't slam it, hopefully it closes it nicely. But it could learn to slam the door based on its experience. So from here, the Nars would then derive a goal to execute that operation slam. And so it's important goals are important for operations so that it's not just executing random operations all the time, but it's also important to drive internal factors, the internal factor of motivation. And it can be used to steer the control process. And because there's many possible things that the system could be thinking about, reasoning about, motivation helps to sort of focus the system on specific pieces of knowledge to what is most relevant to it as a subjective entity. So that concludes the now portion. We're going to go into very, very basic memory and control because I know Bowen will be talking about this. But just to give everybody a sort of surface level understanding of the memory. The memory consists of tasks and beliefs, and a task is a question, a goal, or a judgment. It's something that goal needs to that Nars needs to process. It's a task for Nars to complete, right? And then Nars also has the beliefs, which are the judgments that Nars already processed. So when you input something into Nars, say a judgment, a piece of knowledge, Nars, that'll be a task. And then once it processes that task, it becomes a belief. And the tasks and beliefs are clustered into the concepts, which again are named by terms. And then the concepts themselves are prioritized using a number we call priority. And then NARS can select concepts based on which is the highest priority at the current moment. And that way it's only focusing on what is very important at this moment in time, as opposed to something irrelevant for the current situation. And if you like, you can visualize the memory as a network where every concept is a node with some term attached to it, some word. And then the relations between the concepts, you can represent them like links. Or like weighted links where they're weighted with the truth value here. And remember, this is frequency. This first number is frequency. And the second number is confidence. So this helps you to visualize the NARS memory. Then finally is the actual algorithm. How does like NARS operate? So this is called the control strategy. It's still an open problem. And different NARS systems can have different control strategies, and they might be better in certain domains. And so in each step, the task interacts with the belief according to the applicable rules. That's the same within basically any NARS system. But how those tasks and beliefs are selected is called the control strategy or the control mechanism. And traditionally, they're selected probabilistically, biased by their priority, which means that concepts have certain priorities. And so higher priority means higher chance to be processed by the system. And that's the control strategy. And various factors then influence that number priority. So like how useful was this concept? How relevant is this concept right now? And so on. And that's it. So if you want a full dive into non-axiomatic logic, this is very surface level, but there's a wonderful book called Non-Axiomatic Logic, a Model of Intelligent Reasoning by Dr. Pei Wang, who's here, the creator of NARS. And it's a beautiful book, so I highly recommend you read it. And this will take you through the design and justification of now levels 1 through 9, along with the interesting discussions behind NARS and the relevant mathematical theorems to justify the logic. And this is a must read for anybody who wants to do research with NARS. Awesome. We're pretty much right on time. Thank you very much. And next up is Rowan.
Okay. Hello everyone. Glad to be here. And my name is Bowen Xu. I know my last name is hard to pronounce in English, so you can also call me Bowen too. I'm currently a PhD student at Temple University as a member of Temple AGI team. And so today, in my part, I will introduce the design and the implementation of NARS, as well as how to use open NARS to do some reasoning with some simple examples. I will firstly introduce some core ideas of the control mechanism of NARS, and then some ideas including the budget, memory, and working cycle. And then the newest version of OpenNARS, it's OpenNARS 4.0.0 that is implemented using Python. And after that, I will just show you how to install get started with the newest version and how to use it to do some reasoning. And okay, now let's get started. So generally speaking, the system consists of 3 parts. And the first one is the language of the representation. It's called Narcissus. And anything which can be represented as Narcissus can be recognized by the system and handled by the system. And the second part is the logic, non-axiomatic logic. And it is suitable for everyday reasoning. And it defines what the truth is, it defines the uncertainty calculus, and as well as some logical rules. And Christian has introduced this part, so I will focus on the third part, which is the control mechanism. And the third part is non-axiomatic reasoning system, and it organizes a bunch of inference steps all together and can work under the assumption of insufficient knowledge and resources. And today I'll focus on the third part, and that is the control mechanism. And though it's impossible to go through too much details, but I hope I can give you some basic intuitions, and you can roughly know what is going on inside Nars. And to understand why Nars is designed in such a way that is different from designing a special purpose system, we have to start from the working definition of intelligence. So by definition, intelligence is the capacity of an information processing system to adapt to its environment while operating with insufficient knowledge and resources. Here, with insufficient knowledge and resources has a special meaning. It means the system must be finite, open, and operate in real time. So being finite means the system's information processing capability is roughly a constant during any period of time. And being open to new tasks means to make no restriction on the content of a task as long as it can be expressed in an acceptable form. And for the system to live and work in real time means that new tasks of various types may show up at any moment, rather than just come only when the system is idly waiting for them. So to be open to new tasks, as long as a task can be expressed as a Narcissus sentence, then Nars can handle it. So it's easy to understand that Nars is open, right? And to be finite, the capacity of the memory is limited. That is to say, the numbers of concepts, of tasks, beliefs, etc., are finite, no greater than a certain maximum number. While to work in real time, a task is handled once a time within a working cycle, and multi-step reasoning is executed through multiple working cycles, and new tasks can be handled at any period of time. So how is the point 1 and point 2 realized in Nars? And what does a working cycle mean? So let's explain it step by step. So firstly, we must understand the fundamental element of the control mechanism, that is the budget. Every task in Nars has a budget that is defined as a tuple composed of 3 members, priority, durability, and quality. And here, priority is what? It is the priority of a task to be processed. A task with high priority tends to be processed first. And the priority of it, the priority of a task is not constant. Instead, it's dynamic. And it may decrease or increase whenever a task has been processed. So durability determines how fast the priority change. For example, at here, the durability of the red curve on the left-hand side is less than that on the right-hand side. So it just decreases much faster. Right? And so more concretely, storage resources are allocated through budget during a short period. An item, which could be a task or concept and so on, with higher priority tends to be preserved, while that with lower priority tends to be forgotten. And during during a long period, an item with higher quality tends to be preserved, since priority ultimately decays to the quality, right? And during a medium term, an item with higher durability tends to be preserved. And since with a higher durability, the priority will just decay slower. And also, an item's processing time is determined by the budget. During a short term, an item with higher priority has a greater chance to be processed. And because it has a greater number of time to process. The more times an item is processed, the longer the total processing time the item is. And so as the other two cases. So in a nutshell, budget is all you need, although it's a kind of joke. And budget determines the amount of processing and storage resources allocated to an item. Here, an item could be a task, concept, or others. And it's exploiting the budget. There is a data structure which can make sure the memory is finite and new tasks can be handled at any time. So I will introduce this data structure. The data structure is called bag. A memory is a bag that stores a collection of concepts. And here's what a bag looks like. Here's a bunch of buckets. Each bucket is a list that stores tasks corresponding to a certain level of priority. For example, a task with priority 0 is stored in the first bucket, and while a task with priority like a 0.021 is stored in the third bucket. So there's a pointer which points to the non-empty bucket with the lowest priority, and the default value is 0. And whenever an item is put into the bag, it is inserted into the corresponding bucket, and the item container simultaneously it is inserted to the item container, right? And here the item container is a kind of data structure of dictionary with a maximum capacity. So what does it mean? So when there's some room for storage, so the item is added into the item container directly. And after a period of time, the container is full. Then at this time, if a new item needs to be inserted into the container, into the bag, it will be overflowed. So an item in the bucket with the lowest priority will be removed, so that the new item could be inserted. And the bucket, which is pointed to by a pointer, we might as well call it the current bucket. So whenever an item should be picked out from the bag, an item is picked out from the current bucket. And then the pointer has a certain probability to stay or move to the next bucket. And the probability is determined by the level of the bucket. For example, for the first bucket, the probability to stay is very low, but for the last bucket, the probability to stay is very high. So this is how the pointer is working. And okay, and an item is picked out for processing, and it is then put back afterwards. So the priority of the item should be changed towards the quality to some extent, and this extent is determined by the durability. And so now let's go back to this page. A memory in Nars is a kind of bag, and so that a concept compete with each other, and some concepts are eliminated according to budget and the bag data structure mentioned before. And in the meanwhile, you may understand that a concept in the bag with high priority has a greater chance to be processed. So given the data structure, the next issue is how to organize the multiple inference steps altogether. So this figure shows the architecture of Nars, and there are many channels as the so-called mind-body interface, and so that the system can interact with the environment, and all the external inputs and the internal conclusion derived from an inference engine are put into the so-called overall experience buffer. And the content in this experience is put into the memory. And tasks will be just like conceptualized. Some concepts will be constructed. And tasks in the internal experience buffer are competing with each other. And also tasks in the overall experience buffer are competing with each other. And within each working cycle, a task is picked out from the overall experience, and then it is conceptualized into the memory, meaning that the concepts corresponding to the task is constructed. So generally speaking, in each of the working cycle, one concept is picked out from the memory, and the related premises like a task and a belief are input into the inference engine, and you can get a conclusion and then just do the next step inference. So in the following, I will show you concretely what's going on by using some animations. For example, how does the system handle the task of judgment? For example, we have a judgment, say bird is an animal. And firstly, it will be input into the overall experience. And then we take out the task and put it into the memory. Since the memory at the beginning is empty, so we just construct a concept, which is bird is an animal. This whole thing is a concept. And then we put the task into its beliefs table, because since the task is input to the memory, so right here the task becomes a belief, and this concept is linked to this task, and we call this link a task link. And also, since we have bird is an animal, and there's a bird here and there's an animal here, so we need to construct other two concepts, bird and animal. and some task links are also constructed. And also we just build some links between the concepts, and these links are called term links. So which represent the relations between the terms, the concepts. And then after the links are constructed and concepts are constructed, the task is put back to the overall experience. So after some time, we have constructed a network of concepts. And then, so how to do an inference step. So in each working cycle, we just pick out a concept, and through the term link and task link, we can get a task and a belief. For example, we get a task robbing as a bird, and we get a belief which corresponding to bird, but there's no belief corresponding to bird, the concept bird.
Oh,
So
there's a question over here.
Oh,
Yeah. So where does the task comes from? From the coding or from the?
it's from some channels. For example, you can see here. We have some channels like Nars channel, sensory motor channel, and so on. And the Nars channel is what a developer can just input some Nars sentences to the system.
All the tasks comes from the developer or?
Theoretically, no. It can be from the developer, and also it can be from the sensory motor channel. Like it can just directly interact with the environment and get some data from the sensors. Yeah, it's possible.
Yeah. So all the data from the sensors are not just evidence.
Derived tasks, I think he's asking about.
What?
Derived tasks he's asking.
Yeah. So you have some original task from developers or sensors, and also given this tasks or given this task and beliefs, you can derive some conclusions through some inference rules.
It's also back into the system as well.
Generate new tasks initial.
Yes. It can just get some derived conclusions, like some task can be derived from the system itself through reasoning. Okay. So in each step we get a concept, and we try to do a inference, but even this task and this beliefs table, we have nothing to get out, because we have nothing to derive. But if we just pick out this concept bird, and then through its task link we have robbing is a bird, and through its term link we get this concept, and a belief of this concept is bird is an animal. So we have a valid task and beliefs that I believe. So we put these two guys into the inference engine, and we can derive the conclusion robbing is an animal. And this task is put into the internal experience. Okay, so this is how generally is how a judgment is handled. So let's see another example, which is a little bit contrived example. For example, we have we have two balls, ball A and ball B, and we have a belief that if ball A is moving left, then ball B will be moving right, and then we have another belief, which is if the system push the ball A, then ball A will move left. And the goal is that we want the ball B to move right. So let's see what's going on inside this system. And firstly, suppose we have had this network, this concept network, and we take a task from the overall experience, which is this goal. Ball B should be move right. This is the goal. And we check if there's any concept here. So we take out the concept, and also we can find a task and a belief. We have this goal and the second sentence, this belief, the second sentence. Oh, sorry, the first sentence. Then we can derive that derive a new goal, which is we want the ball A to move left. And then okay. So and then we focus on this concept, which is if we push ball A, then ball A will move left. And then we can derive a new goal, which is we want to push ball A. So we can see that a goal is derived through a backward reasoning. Okay. So now let's go back again to this page. All the new tasks are competing with each other, and they are competing in the experience buffer, as we can see here, and all concepts are also competing with each other. A new task can show up at any period of time, even though they may be handled with a delay. So this is some basic ideas of how the system runs. And then let me show you some implementations of the OpenR system. And now we have done with the fundamental ideas, and then here are some implementations. Like we usually use this version, OpenR 3.0.4. It's the most stable version currently. And also we have another version, OpenR for application, or we call it ONA. And it is implemented mainly using C or C++, and it focuses on application. And we have a new version, which is OpenR 4.0.0, and it follows the design of 3.0.4, and it is implemented using Python. And this version puts more attention on maintainability of the code. And it will be uploaded to the OpenR's website soon, although it can temporarily available in this GitHub page, the third page. The project is composed of 3 parts: the Nars parts, the logic NAL parts, and Nars parts. And the first part, Nars, implements the internal representation like term, statement, compound, truth, judgment, and so on. And also it implements a syntax parser. And the logic part implements some inference rules. And the control part, the third part, it implements some data structures like concept and back and so on of the control part. as well as there's a reasoner that execute the working cycle. Maybe we can have a break, and then I will show you how to use the newest version to do some reasoning. Okay. Okay. Welcome back. So next, I will show you how to install and get started using OpenNARS 4.0.0. And so this is implemented using Python, so you can just install it through AGI, like AGI default by now. So I can temporarily manage it by now, but maybe I will change it. So like you can install it in your control within this net.
So I will going to share the screen. Your presentation is not on the screen.
Oh, sorry. Yeah, we can use this command to install the Nars 4.0.0, or you can just download the original code and use this command to install some packages. It's temporarily just located in this address, but it will be uploaded to the OpenNARS website, and then you can run this command to execute the control. Like I will show you here. To run the PyNARS Python and run the Python module. So you can start this reasoner, and then I will show you some examples of reasoning. Like this is the nail one rules. Like you have bird is an animal and Robin is bird. Then you can get Robin is an animal, and I can show you how to just use this in OpenNARS. Like you have Robin is an animal. A bird is an animal. Sorry. Bird is an animal, and then Robin is a bird. Okay. So now you just input two sentences or two tasks into the system, and then you can just input a number. It means how many numbers you want to run, how many working cycles you want to run. So I want to run 5 cycles. So it derives Robin is an animal according to this deduction rule. Also, it can derive animal is a Robin according to another rule, but it's much weaker than the previous one. It has a lower confidence. And also I can try this induction rule. Maybe we can restart it. It's Robin is an animal. And Robin is a bird. 5 cycles. You can see it derives bird is an animal, and animal is a bird according to the induction rule. Also, there are some other derivations, some other conclusions according to other rules. Okay, this is the first example. And for the second example, it's about the revision rule. For example, I saw false ones which are white before, but now I see a swan which is not white. And according to the revision rule, since we see the 4 positive evidence, so the confidence is higher than this one. So now I see a swan which is not white because we have only 1 evidence, so the confidence is 0.5. And that's inputted into the system. swan is white. If you want to input the truth value, you can use this percent symbol. And for example, we have frequency is 1.0, and the confidence is 0.8. And then we input this sentence into the system, and we input swan is not white. Say it has a frequency of 0.0, and the frequency is lower, it's 0.5. And then you can see it outputs the conclusion that swan is a white with a frequency of 0.8 and with a higher confidence than the previous two. Okay, and for the third example, it's more complex. Robin is a type of bird or a type of swimmer, but robin is not a type of swimmer. The first sentence is like this: robin is a bird or swimmer, and we have some evidence to support this this belief. So let's input this sentence into the system. Robin is a bird or swimmer. It has a truth value of this. And then robin is a swimmer. It's not a swimmer. So it should have a 0.0 frequency and 0.9 confidence. And then we run some cycles. You can see here, robin is bird with this a very high confidence. With them as this. So it's kind of we get this conclusion according to a certain rule in non-axiomatic logic, but I'm not going to go through too much details on these inference rules. And for the next example, it's NL4. So we have the belief that an acid and a base can have a reaction. So it can be expressed as this form. Let's try it. An acid and a base has a relation of reaction. The relation between acid and base is a kind of reaction. And the default truth value is 1 and 0.9. Okay, that's run like 15 cycles. Okay, you can see the outputs is this and this. It's the first sentence means acid can react with base, and the second sentence means a base is something that has a reaction with an acid. And for the last example, like it's about the goal realization. For example, we have I wish to feel good, and it's a goal. And we have a belief that if I'm not hungry, I would feel good. So we can just represent these two sentences into Nars as just like this. Self is good. We have self is good. It's a goal. And we have if I'm not hungry, then I'm good. So we have a negation. Self is hungry. And this symbol means negation. If self is not hungry, then self is good. Okay. Now we have these two beliefs, and then let's run 5 cycles, and then it will just get a new goal, which is self is not hungry. This is the goal which is derived. Okay. This 5 examples looks simple, but you can just see, yeah, it works in this new implementation. And then also there are some to-dos. Some of them are listed here. The first is to implement the event buffer proposed in the newest technical report, and the second is to implement some demos like Pong game or Fighter Plan, which is also implemented in other versions, but haven't been implemented in this Python version of Nars. And also, I would like to accelerate the program through C or C++. I just want to implement the Narcissus and the logic parts using C or C++, but implement the control part in Python so that you can just modify the code more flexibly. And also, I need to refactor the code of row table. It's kind of a messy. That's all. Maybe I hope I gave you some intuitions of the implementation and design of OpenNARS, and you can just do some simple experiments using this Python version. And later, maybe Patrick will just show you some demos using his implementation, namely ONA, OpenNARS for application. Okay, that's it.
Thank you, Bowen. So we've seen how Nars can handle encyclopedic knowledge, sentences, describing general facts about the world, things like dog is an animal, bird is an animal, or raven is a bird, things like this. But what about using Nars in a real-time application, especially these days with the other AI systems, especially very impressive AI systems, are doing tasks in real time, or things that require things like dexterity and speed, like playing soccer, playing virtual games that are like real-time video games, things that require thinking fast, things that, and this is the type of thing that traditional reasoning systems do very poorly, because usually they get stuck in long chains of reasoning. Now this is something Nars can handle. So we're going to discuss how to get your Nars to play Pong. So creating your first real-time application with Nars. So as we saw before, Nars can learn from the encyclopedic knowledge, and it can do lots of reasoning on that. And usually it's not a problem, because if we simply want Nars to derive new knowledge and we don't have any time limitation, time pressures, then we can just sit back and wait for the system to finish up its reasoning and then ask the question. But can Nars also learn to cope with fast-paced applications like a video game? Yes, because unlike the traditional systems, Nars doesn't get bogged down in these long chains of reasoning. An example of that would be Shaky the robot, one of the first computer vision systems and in a robot. That was one of its primary issues, was that it would be assigned to do a certain task, like move somewhere, and it would get stuck in a long chain of reasoning. That was one of the primary issues with Shaky. Nars doesn't get stuck in long chains of reasoning because it's constantly reasoning incrementally. So it only performs a single reasoning task at a single time step, and then it can move on to the next reasoning task. It doesn't follow a chain. It selects from all over its memory probabilistically. And also, it has a temporal component to the logic. We talked about events. So it can do temporal reasoning. So what we can do is, in a real-time application, you attach sensors to your system, because you won't be sitting there typing in real time. You cannot type fast enough. So you need to have some sort of algorithm or sensor which will input into Nars certain events based on whatever the sensor is picking up. And so the sensors will input events into Nars regarding what's happening outside in the world. And then similarly, you attach motors to Nars so that Nars can interact with the world. And then using the temporal reasoning, Nars can associate its various sensations from its various sensors to form generalized knowledge about the world. And then it can use this knowledge in reasoning to inform its motor actions. So we're going to walk through how to use Nars in a real-time application. Pong. This is an example of Nars playing Pong. Nars is the one on the top, and that's me on the bottom. And as you can see, the paddle actually follows the ball. It does a pretty good job of blocking it. And on the right, you'll see the it says ONA operation. At each moment, that's the operation that Nars is currently executing. And so for any real-time application with Nars, first you select the application. We selected Pong here. Then you want to identify the role of Nars. So in this case, we want Nars to play the Pong. So Nars is the Pong paddle. And the goal of Nars is to block the ball from passing it and getting into the goal. So according to the above, we give Nars the goal that we want, which in this case would be Nars wants to block, or self inherits block. Then step 2 is to hook up the sensory motor interface. So first you determine what is the embodiment in the first place. In this case, it's a Pong paddle, and we have 3 sensors indicated by these lights that are on the paddle. And one of these will light up depending on the ball direction. So if the ball is this to the left light goes on. If it's the right light goes on. If it's right in the center of the paddle, the center light will go on. So in that sense, we have one sensor, like a position sensor for the ball, and it has 3 possible states: left, center, or right. So at any given moment, the sensor will be inputting left, the ball is left, the ball is center, the ball is right. On the other flip side is the motor. So this is the Pong paddle, and similarly, there's 3 operations. So the system can move the paddle to the left, it can stop, or it can move to the right. And so, like I mentioned, the sensory information is not going to be in Narcisse like natively. You're going to have to write some sort of conversion algorithm where whatever the sensor is picking up, it becomes a Narcisse sentence, and then input that into your Nars system. So for example, if the sensor picks up, we have an algorithm, where's the ball? And then, we detect the balls to the left. So the sensor is detecting the ball to the left, and it might enter this event, the system, ball is left. So the system is now getting sensations, and then you also want to input your motivational signal, which would be that goal we talked about earlier. And so you want to be supplying enough, you want to be supplying this goal to make sure the system remains focused on solving that goal. And then finally, you run the application. So what's going to happen? First, Nars as we mentioned, the memory is completely empty when it first starts out. It doesn't know anything about the world, so the system has to first explore, makes mistakes, and then learn about the world based on its sensations and its motor actions and the associations it makes, the sensory motor associations that it makes. And the way it explores is through what we call motor babbling. So what this is sort of like a baby babbling. Nars automatically triggers its motor operations, despite the fact that it's not really certain what these operations do, but it will try them out. And based on the sensations it receives after trying these motor operations, it can then make certain associations and derive knowledge saying, okay, I triggered this motor and this sensation happened. So maybe whenever I do this action, this event happens. And if you're going to be running experiments like this, you can't just let Nars run and expect magic to happen. You need to observe the application and try to think about what is Nars receiving and what is it doing internally so that you can really gain an understanding. And that's the beautiful thing about Nars is that it is human understanding. So you think about what Nars is doing from a human perspective, and it's not a black box. If the system is acting up, there's a reason for that, and you can determine the reason. So, for example, sometimes like there are random factors in Nars, and also randomness in your application, like physics for certain physics applications might have a random component. And it could result in a situation where Nars doesn't get the opportunity to learn the behaviors that we want it to learn. So, like in this Pong game. You can see the ball sometimes will get stuck like on this wall, start just bouncing back and forth, and then it gets kind of stuck. And so in that case, Nars will just babble back and forth, and it will never receive any sensations about the ball hitting the paddle. So we can get we can watch a video about what this looks like. So right now, Nars' memory is completely empty. Nars is the paddle there at the bottom of the screen. And you see that the paddle lights up depending on the position of the ball. Now, every once in a while, you'll notice the ball is going to hit the paddle, and that's what we want. That's the goal of the system. And on those coincidental moments, Nars is going to learn, it's going to be babbling. It's going to say, the ball was in the middle, I stopped moving, and the ball hit the paddle. And it's going to learn, okay, whenever the ball is in the middle of the paddle, I need to stop moving, and then I'll hit the ball. And over time, very, very quickly, Nars learns to master Pong. I mean, Pong is a pretty simple game, but based only on this motor babbling and these very simple sensors, that we're not inputting an image or anything, it has these simple sensors, it will learn to play Pong. So you watch, and the paddle will almost perfectly follow the ball after a couple of iterations.
Does Nars have the tendency to cheat the system, like trying to make sure that it gets like this angle that it never needs to move?
Can you repeat?
Like previously, I've been watching some AIs that will try to like cheat the game in the sense that like try to find the angle that makes the ball just go back and forth, so that it doesn't have to move. So make sure that it makes the least movements to have the maximum.
Well, that would be the optimum solution, right? So, yeah, I suppose that would happen. In this specific case, the ball never really goes up and down like that. It only goes left and right. I've never seen it get stuck up and down like that, although you're right, it's technically possible. But in that case, yeah, the optimum solution would be to just stand still and let the ball just keep going. You're right. So let's analyze the clip. Through associating the sensory events, Nars learns that when the ball is in the middle and it stops moving, the paddle will block the ball. And it does this through conjunction and temporal induction. So the conjunction's happening here. The sensor is saying the ball's in the middle. The stop comes from the babbling, and we can put them in conjunction. These are both happening at the same time, so you can say and like these are both happening. Then suddenly an event is received later that the paddle was hit, and so we can use temporal induction to form this implication statement. So if the ball is in the middle and I stop, then I hit the ball. Very simple. And since that is the predicate here is the original goal, if you remember that's what we're inputting, then you can use inference to derive a goal for this subject, for this conjunction, and that becomes another goal, whose completion leads to that goal, according to the implication statement. And so because stop is an operation, it's controlled entirely by Nars. So if we desire stop, we can just stop. The only goal now is to get the ball in the middle. So Nars will derive, I want the ball in the middle. Then by further motor babbling and association, Nars learns the ball is left and I go left, then the ball becomes in the middle, which is what we want now. Or if the ball is to the right and I move right, the ball is now in the middle, which is what we want. Again, temporal induction and conjunction derives these goals. We can simplify with the motor ops out of there, which just gives us, when we receive a sensation that the ball is left, it will simplify this term out of the conjunction, leaving only a goal to execute the operation. And so in that way, when the ball is to the left, Nars derives, I want to go left, and it will do so. And this simple knowledge base will derive or covers all the possible sensations and is sufficient to play Pong. And that's all. Thanks for your attention. And if you are interested in this version of Pong, you can download it here, or I encourage you to download Nars and actually build your own application.
Question.
Yes.
Can it actually derive the prediction of if the current position and speed is like this, so and where should it be at the time of the intercept, so that it won't have to follow the ball every time,
Oh, you're saying it's coming at this angle,
and I need to move here.
Yeah. Because the sensor is so simple, it has no perception of angle or anything like that. All it knows is the ball. This here, here, or here. So the sensors are too simple. Theoretically, you could set it up though that way. Yeah.
The frequency of sensor input that is controlled by the logic that you write, is it?
Yes. And normally you'll just give a frequency of 1 because it's an event that's happening in the world. So you say this is true, like this is happening. But you might not give it a very, very high confidence because like we mentioned, once you saturate out the confidence at the maximum level, you might run into issues.
I meant to the frequency at which you will input the sensor input.
Sampling frequency.
Oh, yeah. It depends on the temporal resolution you want for your application. So in this case, I'm inputting every third of a second, which is sufficient because the ball, every third of a second, it won't move very far. But if the ball was moving, say, very, very quickly, I might want to do it 10 times a second or 20 times a second. So it really depends on your application.
Okay, thanks.
Any other questions?
Yeah. So is it possible, or well, probably it's not possible yet, but how would you pursue something like if you want to motivate additional? Oh, you're doing a really good job now. Not
Can you
motivation, but from kind of third party.
Sorry, can you rephrase?
Is it possible to? Would it be possible to motivate Nars agents does a good job, not by observing the environment, but by kind of social.
Oh, like a reinforcement sort of, or like a reward?
For instance, yeah.
The completion of the goal itself is sort of the reward. So when the goal is not satisfied, the system is going to be working really hard to figure out how can I satisfy this goal. And when the goal is happening, like if the ball hits the paddle, then the goal is now satisfied and NARS won't process it anymore. It says, okay, I'm done with it. This goal is complete. I'm done. And it can move on to the next one. And so you could have various motivations, and then it will go focus on the next motivation.
But it's not possible to have two motivations at the same time?
Yes, it will. It will flip between them, or if one goal is very important in the current moment and the other one not so important at the current moment, then it will focus on the important one and then leave the other one. But if, let's say you have two goals, like if you want to do two different things at the same time, then it will alternate between, perhaps. Yeah. Does that answer the question? Great. Yeah.
So I don't know if I've understood correctly, but it sounds like you would get because it's prioritizing things, and it's not going to get stuck in all kinds of everything. It's based on the system. You're basically, well, you give it so many inputs, it's going to process things so many times. So if you sort of, I suppose, can you increase the sort of frequency with which it sort of perceives and processes things, and does that affect the results meaningfully?
Like you're saying, can you speed up the NARS?
Yeah, basically.
It'll go as fast as your computer goes. So you get a faster CPU, you can speed it up. Yeah. You can also arbitrarily slow it down if you, for some reason, wanted your system to run a little bit slower.
Did you do any experiments with that? Did it change the outcomes a lot?
Let me think. Yeah, so I did put a couple of delays in between. I actually slowed down the system a little bit. I found it helped it work better, simply due to the event logic. So the events decay, the confidence decays over a certain amount of time. So like to have the events decay more quickly was better in this case.
Wow, that's cool.
So you do have to tinker a little bit. You can also set up like an automated system to change the parameters, perhaps like an evolutionary algorithm to optimize those hyperparameters. That way you don't have to tinker yourself.
Yeah.
Good question.
Yeah.
In the previous slide, you had like these concepts like ball left, center. Which of these are like pre-programmed, and which does it learn by itself?
So this is pre-programmed.
Yep.
Because that's coming from the sensor. Okay. This conjunction here is learned by the system, and this whole implication is learned automatically by the system. And it does that simply because these two events occur at the same time. So we can do a conjunction, because we're saying this and this, right? And this happens afterwards, so we can say if this, then this.
So on that point, roughly how many inference steps does it take to learn these things? Okay, do you have an idea? Like, is it like how much babbling and how many inference steps? I'm guessing thousands, 50,000, or?
In terms of inference steps or working cycles, I can't be sure.
How about time? How long does it take?
So based on the video, I sped up the video a little bit. I think it took like 3 or 4 minutes only. But that's in very optimal conditions. Like I said, sometimes the ball will, not do exactly what you want it to. And sometimes the system will make incorrect associations like, oh, I babbled right. And then the ball was left, but it was coming at this angle, so it hit me. So maybe now the ball's left, I move right. It's going complete opposite direction, and which is incorrect. We don't want that behavior. But, due to the perception of the system and its limited sensors, it might make those incorrect associations. And then it would take longer, like 10 minutes or so. But, eventually, with enough revisions, it will get to the right place.
It's probably more a factor of the physics of the game, right? Not the speed of the component.
Yeah, and also the like resolution or intricacy of your sensor.
Right.
Yeah, if you run the owner Pong demo, it runs so fast that you can't actually visibly watch it, and it will learn it in a few seconds. So this is highly constrained by the speed of the graphical UI.
Yeah, that makes sense.
And also, is if the ball is doing what you want it to or not.
Are you considering additional experiments where you add complexity, obstacles, you add, or are you kind of considering this a dead?
Well, I was considering adding different sensors. For example, this is only left, middle, right, but maybe something like top, middle, down. Or, like adding quadrants, like when it's in this quadrant, then light up that sensor or event. So you can have like 9 different sensors. And so kind of increase the resolution.
Right.
Doing something like inputting the entire visual image is still out of the question.
Yeah.
It requires further research, but
maybe the paddle could move not just in the line, but maybe a little bit of, you have some obstacles that the paddle require, learning to move around a little bit.
That'd be a different game.
Yeah,
maybe.
different game.
You have to design the game, but yeah, of course.
Well, they're minor changes, right? But you want to just add some complexity, I think.
I agree completely. And that was my idea for the next step, would be to add something like quadrants for sensors. I just have not gone to it. Thank you.
Thank you.
As for the assumption of limited knowledge and resource, the limited knowledge means at the beginning is know nothing, and does the limited resource just mean the limitation of the sensor and not the inside computational power?
So when we say insufficient knowledge and resources, it just means that the system will continuously learn, and it it won't assume that it has all the knowledge that it needs. It's going to be taking in various pieces of knowledge, even things that are of lower priority, things that it might not normally consider for optimality. It might try different things that might not be considered optimal, that might later be found to be optimal. So when we say insufficient knowledge, it's more about the system continuously learning.
What about the resources? It's just the limitation of the sensor, or include the
resources? Insufficient resource.
Yeah.
In that sense, we're just saying the system can't. We can't ever guarantee that the system will be able to have all the resources it needs to solve a problem. Sometimes it needs to think about a certain problem and then move on to the next one. Otherwise, it will, like I mentioned about Shaky the robot, which was had issues because it would get stuck in these long chains of reasoning. We can't assume we'll eventually get to the end of this chain or anything like that. We have to say, okay, we'll do a single step of this, but we're not sure if the knowledge is sufficient to fully solve the problem. So we might go focus on other problems. So it's really about resource allocation, computing resource allocation.
Because in this demo, I cannot allocation of computing power resources.
It's not necessarily with the demo. It's more an assumption about Nars itself, more like a theoretical design assumption. If it helps you to just disregard that and just focus on the application, it might do that. But in terms of design and theory, then that's important.
Did I understood it correctly that NAS can't deal with numerical values at all, like quantities, coordinates, all this stuff?
That is something we're experimenting with. Patrick, I know, has experimented with quantities using numbers as terms. So it might have a concept for a number, like concept 1, 2, 3. And then it can use those as terms of reasoning.
Yeah, with operations.
Yeah. And we've also experimented with using truth values to represent quantities, but that's still experimental. Good question. Oh, a lot of questions. I love it. Very good. All right, well, if that's it, then we will move on to the next part, which is Patrick's hands-on example.
So, I think before we dive into the hands-on example I wanted to give you, I just want to give you also an overview of what happened in the last years with this project, where it's heading. If we look back, I'm here at Stockholm University since September 2021, and I have actually this implementation which Christian just showed. Openness for applications has been developed since the first release was 2020, but it has really taken off from taking a lot of ideas from openness and trying to build a NAS system which can be effectively used for various application purposes. And a lot of these ideas which contributed to this system were actually back in my PhD. During my PhD with Dr. Bai Wang, and I had the honor to be his PhD student and to develop many ideas which made this this implementation possible. And I also have to say a huge thank you to Hugo Latterby, who funded us over many years and made this project possible in the way it currently is. And there's really, with every technology, it needs some time to develop, to really unroll its application potential. And I think the same is true with NAS. And during my PhD, it was especially a big focus on sensory motor, since personally, for me, I was always convinced that that to go to a human level is not a piece of cake. And even in animal kingdom, we see animals which can do very impressive feats and adapt to new situations and cope with various difficulties they face in their environment, learn to adapt to them in ways I wouldn't even have imagined that a bumblebee, for instance, could learn to put a bore into a hole simply from observation. It's not even reward-driven learning in this case. It watches another bumblebee, and from this learning from observation, it's able to do this behavior. And for me, as an AI researcher, I want to make sure that on the way we are trying to take, that we will actually be able to explain some of the capabilities which are demonstrated by various animal species. And that's actually not that trivial to make sure that we actually cover these abilities. And I think a major aspect in this regard is to look back. What do we really need? What does an AI system really need to have to be able to explain the capabilities which we can see in nature? And I think a large part of this is if, for instance, in machine learning, there's a lot of focus on reinforcement learning. It's really great work. But we also have to look at what do we actually need? Is there maybe more to it? Are there some phenomena which we also need to explain? And for me, during my PhD, it was especially when I worked at sensory motor that I noticed the importance of causal relationships, that an agent can actually learn behaviors which not only lead to a certain reward value, but actually to an understanding about what would happen in the next situation. What happens if we do a certain thing in a certain situation? What's the consequence of that? And this is a major part of learning from observation, because if you learn from observation, there is no reward just yet, but there's already a lot of information you can take in and then utilize in the future to make certain outcomes happen. And for years, it was really just a struggle with sensory motor. How to even get the most basic learning abilities to happen in the machine, things which are started with insects and with mice. And I was really into this thing and trying to make this happen in the machine. And there was this kind of background assumption that, yes, maybe we want causal relationships, we want some way for it to learn behaviors where the system really learns to model what's the consequences of its actions in different contexts. And since then, the Nars project has really gone a long way with various robotics applications where we can actually demonstrate some of the reasoning abilities which are studied with animals. And that's, at least I can say that over the years, sensory motor is something which works really well in NAS in the meanwhile, even though it started as a model which is mostly concerned about the like conceptual reasoning. You have seen today the introduction of the non-axiomatic logic levels. And for many years, we had implementations which could really reason very well on declarative knowledge, yet couldn't yet act in the real world because certain sensory motor capabilities were not yet present. And in this regard, the project has made really big breakthroughs in the recent years where we can really say, yes, the system can reliably learn sensory motor behaviors, even in situations like real world situations where it needs to apply them. And that's a huge breakthrough, of course, from the perspective that sensory motor is somewhere at the bottom of human level AI. It's of course still a small step, but it's a step that at least I always thought to be necessary to get to human level AI. Of course, there is some disagreement whether to what degree sensory motor capabilities need to be present in an AI system. But at least this part is working relatively well in the meanwhile, with various examples where we can actually demonstrate this. And more recently, we have focused more on the relational reasoning side of things. Like if we look back at this slide with the animals, like here, Alex the parrot, you might know this kind of parrot from Irene Pepperberg's lab, which is able to answer questions about objects. In English, it's not really mastering human language, but it has learned to some degree the meaning of certain words it gives. Like it can really count how many green objects are on the tray and give you an answer to that. So even though it doesn't have the human language capability, it's able to have some kind of correspondence between the words and the things it sees, so it can actually answer the question. And Irene Pepperberg really showed in her study that the parrot it's not simply parroting, but really understanding what it needs to answer, really the essence of the information that is asked about, that it can actually find the right answer to the questions. And from our perspective, okay, sensory motor, if this is there, then the question is, how can we reach the other capabilities? How can we get verbal abilities inside relational reasoning on a high level? And there's still a lot to be done, but also there we had progress. You will see today in the afternoon, where, for instance, we have combined our system with large language models, where we essentially try to combine the strengths of both approaches, so that essentially the large language models are used to translate English sentences into this formal language of the system, and then letting the reasoning system carry out the reasoning reliably, and so that question answering can then be performed on natural language input. So we also made some progress on the more human level end of this story, but also on perception and sensory motor. There's of course still work to do, but this is where we can really say we closed really a gap in the recent years, which was that like 2014 and earlier, you could not expect back then that Nars could, for instance, learn to play a computer game. But now you can do various things with the system, and I will give you some hands-on examples so that you can also see how you can actually utilize the system in various applications for yourself. And also, since it directly connects to what Christian has shown with the Bong application, there was this question, can it actually handle numeric input? Can it actually not just have this left, middle, right, but could we actually feed the position, for instance, into the system? Could it do something with that? And we have an example which we call the band robot. The visualization is maybe a bit lacking, but what you can see here, this is a robotic arm. This is the object to pick. This is the position it has to drop it at. It's started from scratch, empty memory, it receives the location of the arm, the location of the target, and the target location and the location of the object to pick. And we will see it does. It's actually also just a matter of seconds or sometimes minutes for it to learn this task. So you see now this learning process unfolding. Hopefully it will work. Built various of this hypothesis, which Christian has shown, which is like a precondition, action, consequence, and in this case it's relational, of a relational form, because it needs to compare what is the location of myself, what is the location of the object, what is the difference? Is it to the left? Is it to the right? So in this case, it's not information we feed it, but it's information it derives from this numeric input information. So we have also made progress in allowing this reasoning system to obtain numeric information, like from sensors, building comparative relationships on top, and then utilizing these comparative relationships for both learning and decision making. So here you see this process. It looks like it has already, maybe not yet mastered, but pretty close of sometimes exploring and doing water bubbling, but it got the essence of the task, that it needs to put this into the hole. So you can see this has learned this task and has now done this in a way that relational knowledge is utilized, and this relational knowledge was not given to it, but it has built this on its own. So this goes directly to this notion of extending sensory motor capabilities with higher level reasoning abilities, so that we can, for instance, explain things like this, where the bumblebee learns to put the boar into the hole. And that this is, of course, a simplified version of this task. It has some parallels. It's, of course, simpler from a perceptual perspective, which is also the reason why we are also exploring our work in the context of robotics, to actually show and demonstrate that this is not just something which works for a simple simulation, but you can actually use this capability for real-world applications. Question?
Yeah, could you maybe go a bit more in depth how the sensory channel looks like in this example? Like what kind of data is being fed into Nars?
The good thing is there will be, this afternoon in the workshop, we will go into all these advanced capabilities, which we have developed in the recent years, like sensory channels and how to connect with sensors and actuators on real hardware, and also various topics like how to make the system scalable. Like it's one thing to have a reasoning system which works for a few toy examples. It's another thing to set it up in a way that it can continue operating, having persistent memory, potentially multiple reasoning instances operating on the same memory, on the same kind of graph knowledge database, so to speak, and essentially making a system which can run reliably over a long time period, which is really also the idea of Nars is that it will not just be restarted every time solving a simple problem and then getting deleted and reinstantiated for a new problem, but we really want to get to a stage where this system can run for years, essentially, learn new information and extend its knowledge for various applications, essentially. So we are getting closer to this goal. You will see in the afternoon that we have made big progress in terms of how to have persistency of memory, how to connect with robotic actuators and real-world sensors, and how we actually encode the sensor information. We will go into some of the details this afternoon. I just wanted to give you a good overview of what has happened in the recent years for this project, and also, of course, keeping the long-term objective in mind. This is actually meant as an AGI project, which at some point ideally would run for years and keep learning new knowledge and improving its capabilities. So that's this part. The other part of what I wanted to show you is how you can actually utilize the system for your own purposes. The first part here is how to download and install the system. You can simply get it from GitHub. So if you have like a new directory, you can.
The text a bit bigger, please, Patrick.
Oh, the text is a bit small, I have to admit. So we're in a new directory, so we can now. Is this better? Is it still a bit smart? So you can simply clone the project. And then you enter its directory. There's a build script which you can run. Build.sh. It's on a M1 MacBook. It will tell you there is no such thing as SSE, but like a processor extension for processors, Intel processor architecture. But here it will just proceed with compilation without the flag. So the warning should not concern you. It's just telling you that SSE is not present on your processor, but that's fine. You have a M1 MacBook or ARM processor. So if it has compiled it, and if you start the generated executable, then it will run tests, and it will ideally will tell you that all the tests run successfully. So at this point, you should be good to go. So it's really straightforward to get started with this system. You just need to clone it and execute the build script. You will need some C compiler, GCC or CLang, and then this will work. In terms of using the system, it depends. If you simply want to interact with the system, there's something called the shell. So you simply pass shell to the executable. You can also colorize it by piping it into the colorizer script so that you get nicer output. Like if you say cats are animals, still a bit small, right? So this is what we input, and it says it has accepted the input. And also ask it questions like what is an animal? And it will say cat, for instance, is an animal. So this is just how you can start up the system and interact with its shell. But maybe if you're interested in how to utilize the system in application, then it's also quite straightforward. You can create a new Python file and put it into the MISC Python folder of the project. And then you can just give your Python file some name, just one.py. And all you need to do is execute this line, and you will already have the system running, and you can already say what you want to input to it. And the way you provide input is via this add input function. So you can simply say now add input. So we can do the same thing with it here with the shell, but this time we use the Python interface. So if we do this, if we execute the script, so MISC. Run. Do the same thing you saw before in the shell. You will also get this printout. If you don't want the printout because you're maybe creating a shell applications. Maybe you don't want it to print what you have input, then you simply put print equals false here, then it will not print it. And what you can do, for instance, same as there, we can, for instance, ask a question to the system using the same at input, and you will see the answer output here. But maybe we don't want that. We want to make use of the answer in the code for some application. So we again set print equals false. We don't want it to be printed in the shell. So how to get the answer to the question? Well, it's easy. We can simply get the return of this at input. So this will return you a Python object which contains the answer we have seen. So if we look at this, what did it actually return here? You see it's a dictionary which contains the input, which is the input question, and it also has a key in there which says answers. And here, the value of this contains the question, the answer to the question, which is that cat is an animal. So you simply have a Python object which you can use. It's just a dictionary. So we can do this. We can get the answers back. We want the first answer, and if we print this, we're already there. We have all the information, occurrence time, stamp information, punctuation, the term, and the truth value of the answer. Maybe we only want to see the term and the truth value, so we can say the term. So this is the answer, and the term of the answer is simply answer. The term of the answer, and the truth value is the truth of the answer. And maybe we want to print the term and the truth of the answer, so we do this. We wanted the first answer. It told us because it's a list. So we have now printed in our own way the answer to the question and its truth value. So you see it's very easy to utilize the system in a Python program and feed it information and get back answers to questions. And the second, there are essentially two major things you want to do in applications. You want to get answers to questions. And the second thing is you want to see when the system wants to do something, when it wants to invoke a certain operation or actuator. We can also create an example for this. We can input some procedural knowledge. Let's say something like in the robot case, if there's a bottle in the front of the robot and we want to pick it, we want the system to pick it up. So if there's a bottle in front and we pick it, then say the mission goal is achieved. And so if there really is a bottle in front, which for instance might come from some sensor, like if we have an object detection model, we will see the details in the afternoon. So you can have an event like this. And then let's say you want the system to get this mission objective achieved. So we have all the information here. Some window is a bit in the way. But we already see, okay, it executed the pick operation because we thought that there's a bottle in front. So again, it's printed out. We don't want it to be printed. We can again say print equals false. Everywhere here. And we can again get the return of this car. And this one includes the pick operation. So if we look at print, if we print the return value, we will see there is derivations. We are not interested in derivations. We are interested in the
fourth to last line. Further down.
window is in the way. Yes, we're interested in the
It's further down, Patrick.
executions. There it is. Okay, so here you see what it did. It has returned the executions, the operator it has invoked, which is the pick operation. So if we want to get this, since it's simply a dictionary, we can again do executions. If we print this, we get this operator pick. So we're almost there. So you see, actually we are there. So we have what it executed. It executed pick, and there were no operation arguments. One can also have operator arguments, but you see, it's very easy to make the system do something in an application, feeding it information and getting back what the system wants to do, and then having this output operation, for instance, in the application might do then, it can then do various things dependent on what you wanted to invoke. For instance, in the robot case, in this case, you wanted to pick up the bottle, for instance, so invoking actually motor command. So it really depends on the application, what the operation will actually trigger, and it's very easy to interact with the system in the code and to develop application using this pattern interface. So that's a way how the system can be used. Maybe I also want to briefly mention, since it's really important from this roadmap perspective, Robert Johansson, for instance, my postdoc advisor, is using the system to carry out various experiments, psychological experiments, using the system. So essentially trying the system on experiments which are typically carried out with animals and with humans, just to see and to evaluate our progress on this roadmap of realizing more advanced cognitive abilities in the system, and whether we're evaluating essentially how well we are doing on this ladder or roadmap. So, and he is also using this pattern interface essentially in the experiments. That there are also some experiments programs like OpenSesame, which allows you to design psychological experiments and simply invoke the system via pattern. So also there you can simply invoke the system using this pattern interface, so that you can set up an experiment which can both be carried out by the human and also be compared with the system. Which might matter because, interestingly, for us, it was the most interesting cases is when the system's decisions and the system's hypothesis mismatch with that of the human, because this gives some indications either there's something missing, or we do something differently than the human mind potentially. And these experiments allow us to find out to what degree is this the case, in what kind of situations does the system behave differently or utilize information differently. And so that's the roadmap we have taken essentially. Are there any questions regarding the usage of this system? Okay. Then I guess this hands-on part is almost complete. I'm not sure how much time we have left. Another 10 minutes or? then maybe I can show you some of the other examples which are also in this code base. What's really also a design goal of the system is to have a common set of parameters which we use across different examples, essentially. Because often in machine learning, it is a common practice. For instance, you take a Q-learner, you find some hyperparameters which work well for the domain, and for different domain, usually you use different hyperparameters. We force ourselves to find parameters which work well across a wide range of examples. So we don't want the human in the loop finding hyperparameters for the system. We want to come up with hyperparameters which work well in many situations. And maybe there's something I can show there because it's interesting from a theoretical perspective. It's working. So what we have, for instance, been doing, this was actually at the end of my PhD, was to see, is this model actually an alternative to reinforcement learning to some degree? Can it learn these causal relationships or this precondition action consequence relationships reliably enough so that it could, for instance, compete with reinforcement learning in typical reinforcement learning scenarios? And there are a few findings which we found which are quite interesting. And maybe here, for instance, here Bong2 elaborated Bong2. What's interesting about this particular example is it's an example which shows that even in very simple environments, you can break some of the assumptions which are often taken in reinforcement learning. For instance, Markov assumption of the environment and in this case, what we had is we added we have again the Bong scenario which Christian showed essentially, and there is a stop operation. And if the system does not call the stop operation, it will continue going into the direction which it has invoked like a few time steps earlier. So this setting is already non-Markovian because what the system will see next is not just dependent on this thing it has seen in the last step and action it has invoked in the last step. It also depends on what it has done earlier. So it's already non-Markovian, and you see for our system here it's labeled master. This is owner, openness for applications. It's no problem to be in this non-Markovian setting, but if you have a Q-learner which takes this assumption, it will struggle in this domain. Of course, if you change the problem and make it Markovian, then you can get similar results with the reinforcement learner. But it's interesting to see from a generality perspective, if you give a problem to an AGI system, ideally you don't want to find out if it's Markovian or not and then tweak around and somehow make it happen that it can deal with it. Ideally, you don't want to fiddle with parameters, you don't want to fiddle with the input encoding much, you just wanted to learn the task, right? So it's always good if certain assumptions are not made in the first place. So this was interesting to see. But we will see more of this in the afternoon. I just wanted to give you some initial feeling about what we have done, about different things we tried to do essentially, and the progress we have made on this way. That's one thing. I think we have a few minutes left.
Question.
Uh-huh.
Can the system be trained to predict the future scenarios, like in game of chess, for example? If you know the rules of the game, then playing the future scenarios, like if I do this, the opponent is going to likely to do this, or these are the options. And keep thinking forward. rather than just referring to the prior knowledge.
Yes, and also here it's the key is that the system can learn these temporal relationships, which allows it to reason about the future essentially. So as you say, it's able to not only think about what it's currently seeing, but it can also take into account what it predicts about the future. And this is also important. This is important, for instance, in various examples where it needs to plan ahead, where it needs to come up with some strategy which involves future possibilities or even actions of other agents, like in this game scenario where maybe there's another agent in the environment and not only itself. The system is prepared to do that because of this causal representations. From a control perspective, it was only about 2 years ago that we made some major progress in terms of inference control for planning purposes. So essentially, like actually we're in the red folder here, so I can at least show one example here. So in this example, it's essentially just planning what we see here. There's a grid, and all it has to do is to get to the target location. So that's not very impressive in principle, since it's only planning, right? But the great thing about it is this planning is done using Nars, using its ability to learn these temporal relationships and doing that on top of that. And that's powerful because it means if some of this procedural knowledge is wrong, it will adapt to it. It will see it doesn't work. So it gives you both. It gives you this learning abilities, which is really great about reinforcement learning. And it, on the other hand, it also gives you this ability to have a system which can plan into the future what to do and reach outcomes dependent on what it wants to do currently. So it's how to say, so it was to some degree a breakthrough, because also here we don't invoke the system in a certain way here just to make it plan. It's the same thing, the same input, the same hyperparameters, the same system which is invoked here, like it's invoked in all the other examples. So just giving it information, giving it course, and letting it figure it out. And the ability to plan ahead is simply part of its capabilities. So it's not something we as designer have to set up so that it will actually use it. So from that perspective, it's also different from cognitive architectures traditionally, like SOA and ACT-R, which was more like a programming language, essentially running on top of a cognitive structure. Like you have memory structure, different types of memory and so on, but you as a designer needed to encode how to solve needed to encode the problem and which cognitive machinery to use to solve it, essentially. Well, here we just feed it information and we leave it up to the system whether it will plan ahead or whether it will react, make actions more reactively. That's up to the task. Some tasks demand looking into the future further to make good decisions, while other tasks really demand a really quick response. And so it's really task dependent and leaving it to the resource allocation in the system to control what kind of reasoning it will carry out to be successful. That's about this. From a system development perspective, in case someone is interested in how the system is structured internally, we will see in the afternoon like how it's actually working inside. Because of course this all raises a lot of questions. How does it actually do this resource allocation in detail? How does it manage its memory and so on? We will have a more detailed picture in the afternoon with the workshop presentations. And if you're more interested in the code itself, there's also a code documentation available where you can at least see the overall structures and modules which are involved in the reasoner. This is a bit of a traditional implementation. OpenNAS for applications is written in the C language. It's not a very usual choice to write a reasoning system in. Of course, it gives you some portability and efficiency benefits, but it's of course not the first language choice everyone would take. But it's at least highly supported and run pretty much on any OS, or even without OS if you want it to run on a microcontroller. So that's at least the case. I think we are right in time. We are now out of time. It's 12:15. Right. So thank you. And we will